Okay, we're going to be looking at using the moment of inertia in a Newton's second law problem. This is a problem that you're already somewhat familiar with. And let's start by identifying Newton's second law in linear form. And that is simply the net force, or sum of the forces, is equal to mass times acceleration. And also let's identify Newton's second law in rotational form, since we will be needing that. And that's simply the net torque, or the sum of the torques, is equal to the moment of inertia times the angular acceleration. In this case, we must include, or both must be satisfied. We're going to start with a frictionless surface. And here's our diagram. We're going to have a mass 1, which is 10 kilograms on a horizontal surface. It is frictionless. It is connected by a rope over a pulley that has a mass of 5 kilograms, a radius of 0.1 meter. Remember previously we didn't worry about it. We assumed the pulley was massless. That is not the case this time. And then we have a mass 2, and that is equal to 5 kilograms. We want to start the solution to this problem by drawing a free body diagram for each mass, for each object. For mass 1, we draw the free body diagram, and pause the video and try your hand at drawing it. And we have that the normal force acts in the upward direction, the force of gravity in the downward direction, and we have a force of tension 1, the force of tension from the rope, acting it toward the right. And we assume the acceleration is toward the right. Now let's look at the pulley mass. Once again, try your hand at it. Pause the video. And we will have a force of tension 1 acting toward the left at radius r, a force of tension 2 acting downward at radius r, and with an assumed acceleration, angular acceleration, going in the clockwise direction. Now let's look at mass 2. And we have a force of tension 2 in the upward direction, the force of gravity in the downward direction, and an assumed acceleration in the downward direction. And as always, we will take the acceleration direction as our positive direction. Now we can get our equations. Force of tension 1 is equal to mass 1 times the acceleration, and the normal force minus force of gravity equals 0. It is not moving in the horizontal direction. For the torque equation, we have minus Ft1r plus Ft2r equal to the moment of inertia times the angular acceleration. And for the mass 2, we're going to have the force of gravity minus the force of tension 2 will be equal to the mass 2 times its acceleration. Now we want to solve for A. So first thing I want to do is take and substitute for the force of tension 1. It's mass 1 times the acceleration. And we obtained that from the first equation. The next thing I want to do is I want to rewrite this equation as the force of tension 2 is equal to the force of gravity on mass 2 minus the mass 2 times its acceleration. And that is going to be substituted for the force of tension 2. Then I have to relate alpha, the angular acceleration, to A, the linear acceleration, and substitute in for alpha, the linear acceleration divided by the radius r. Having completed that, I can now write the equation below where I have terms involving A and G, but I still have the moment of inertia I, and I need to relate that back to its mass and radius. And that is a tabulated value. I know that that is 1/2 mr squared, so I can substitute that into I. Carrying out that substitution, you can go ahead and do the algebra. Once you do the algebra, you should come out with the following. Pause the video and do the algebra. You come out with A equal to the force of gravity on mass 2 divided by 1/2 the mass of the pulley plus M1 plus M2. And that comes out to be 2.8 meters per second squared. And that's the end of the module.